AP Chemistry, we're on to our second to last lesson of the course. It's called Balancing Redox Reactions. So here are the rules for assigning oxidation numbers. We're going to do a few problems on doing that first. So remember, oxidation numbers are similar to charge numbers that we've been working with for a long time for ions. You have a sheet called Charge Numbers by Ion. You have a sheet called 60 Common Ions. We've been using that for a while. Those apply to ions, to actual atoms that lose or gain electrons. Oxidation numbers are very similar, except they also apply to covalent bonds. Remember, covalent bonds are the two strong guys having the tug of war. Nobody wins, so they share electrons. Water, H2O, is a covalent bond. So water, in a water molecule, the oxygen is more electronegative than the hydrogens. So it tends to pull all the electrons, including hydrogens, towards it, but not totally take them away. And that's what makes it a polar molecule. The negative side is the oxygen side because it has the electrons pulled in that direction. The positive side is the hydrogen side because the electrons are pulled away from it. But what oxidation number does is it treats that phenomenon as though the oxygen was totally taking the electrons away, as though it was an anion totally taking the electrons away from hydrogen. In other words, the more electronegative of the atoms is given the electrons, as though it totally took them away like it would in an ionic bond, even though it's not an ionic bond. So oxygen would be taking 2 electrons away from hydrogen, so that would give oxygen a 2- charge. And we know that's also the charge number of oxygen if you look at your charge number of ion sheet, 2-. Hydrogen would be losing the 2 electrons, so it would have a +1 charge. Each hydrogen would have a +1, +1, so it would balance out. 2 +1s matches up with a 2-. So it's treating a covalent bond, in other words, as though it's an ionic bond, even though it really isn't. So that's what oxidation numbers do. So the rules are elements in their elemental form, most stable form, have oxidation numbers of 0. So hydrogen, for example, a hydrogen atom has an oxidation number of +1. But a hydrogen molecule, H2 molecule, is really the more stable form of hydrogen as a hydrogen gas. That has an oxidation number of 0. Okay, so 2, for monatomic ions, the oxidation number is the same as the charge number. So if you look at your charge number by ion sheet, potassium, K, has a +1. Charge number, and that's also its oxidation number. Oxygen has a -2, 2-. Okay, so that's that. Now, nonmetals usually have negative oxidation numbers. That would be things like fluorine, chlorine, nitrogen, the things over on the upper right-hand corner of the periodic table. So they usually have negative oxidation numbers, but can be positive. So, for example, sulfur, can have oxidation numbers ranging all the way from -2 to +6. So how do you know? Well, that's what we're going to talk about in a minute. Is how do you know how do you determine the oxidation numbers on different elements in a chemical compound? So hydrogen has a +1 when bonded with nonmetals, and the vast majority of the time you deal with hydrogen, it is bonded with nonmetals. So for example, H2O, that's nonmetals. CH4, that's nonmetals. So it would have a +1 in those cases. It's -1 when it's bonded with metals. We're not going to deal with any of those examples. Maybe later in the spring we can talk about some of those, but that's not very common for it to be bonded to metals. So that's a key. I put a red box around that because that's one that I consider that kind of an anchor element. When you see hydrogen, you know it's going to be assigned a +1, and that's what you're going to use to determine the charges of other elements that it's bonded to. Oxygen always has a -2, except in peroxides such as H2O2, where it's -1, but that rarely happens. You're rarely dealing with peroxides. So that's another one I consider to be an anchor. You're going to look at oxygen and say that's a -2, and you're going to use that to compute the oxidation numbers of the other elements that it's attached to. You'll see what that means in just a moment. Fluorine is always a -1. And other halogens, that would be chlorine, bromine, iodine, second to last column in the periodic table, are -1 except combined with oxygen. That's because oxygen's more electronegative and will pull electrons away from them. But so when they're combined with oxygen, they'll be positive numbers. Okay, so we'll deal with these when we come to them. But the two in the red boxes are the one to really focus on for this particular lesson. So here's a couple of chemical equations, and we're going to assign oxidation numbers to all of these. So first of all, cadmium is a 0. It's a pure element. It's in its natural state. It takes on a 0. Now, let's look at this nickel dioxide. Okay, so oxygen has a charge of -2, and there are 2 oxygen atoms, which equals -4. Okay, so we said oxygen's a -2. You have 2 of them. That's a -4. So that's going to help you to assign the oxidation number to nickel. So this makes the charge on nickel a +4. There it is. So that's a +4 because the O2, 2 times -2 is -4. However, this is a trick, and you don't want to fall for this. I have fallen for it. So you want to be sure that you realize that that does not change the oxidation number of oxygen. So this does not change the oxidation number for oxygen. It still equals -2. So you don't put -4 there, you put -2. Oxygen still has an oxidation number of -2. Okay, over here on water, oxygen has an oxidation number of -2. Okay, so hydrogen, that has an oxidation number of +1. We said that on the previous slide. There's 2 of them, so that gives you a +2. And so that balances with the oxygen, which is a -2. However, the oxidation number of hydrogen still remains at +1. That's its basic oxidation number. By the way, it's not an H2 in the sense of a hydrogen molecule, H2, which we said on the previous slide was 0. It's not an H2 molecule. It is a part of a larger molecule, the water molecule. So each H is a +1, so that's the basic oxidation number for hydrogen. Okay, hydroxide. So hydrogen has a +1 charge. There's 2 of them. So that 2 is outside the parentheses. That means you have 2 hydrogens. You also have 2 oxygens. So for the hydrogen, that's going to be a +2. For the oxygen, it's going to be a -2, and you have 2 of those as well because of the 2 is outside the parentheses. So that's a -4. So if you add those, -4, -2, you get a -2 for the overall hydroxide because there's 2 of them. However, each one is still a +1. There's a +1 for hydrogen. There's a -2 for oxygen. So it's -2 + 1 is -1 for the hydroxide. And then the cadmium is going to be a +2. Since the hydroxide total was a -2, then the cadmium is a +2. So again, let's review this concept. The -2 that you computed for the hydroxide, because there's 2 of them, you use that to assign the oxidation number to cadmium. Hydroxide, 2 of them was a -2, so cadmium has to be a +2. However, that does not change the oxidation number of hydrogen, which is +1, or of oxygen, which is -2. Okay, over here we have the exact same thing with the nickel hydroxide there. So 2 minus 4, that gives you -2. So you got a +1 for the hydrogen, the oxidation number. You got a -2 for the oxygen, and the nickel is +2 in that compound. All right, so those are the oxidation numbers. Now determine there's only exactly one element in any reaction that's being oxidized and exactly one element that's being reduced. So which one is which? So find them, and let's go ahead and do that. So there you go. Cadmium goes from 0 to +2. It increases its number. That's being oxidized. That one might not be obvious to remember, but reduced is easier to remember. So reduced is the nickel. It goes from +4 down to +2. So that number is being reduced, that oxidation number, so that's the reduction. So reduction is gain of electrons. The oxidation number is going down. Oxidation is losing electrons. The oxidation number is going up. Okay, now we have another complicated little molecule ion here. So let's read this. There are 7 oxygen with a charge of 2-, which equals -14. So there you go right there. Negative 2 for oxygen. Oxygen is always negative 2, and you have 7 of them, gives you negative 14. The overall charge on the molecule is negative 2. Okay, so let me take that off for a sec. That negative 2 there, you see, 2 minus, is not for the oxygen. It's for the overall Cr2O7 molecule. So the overall molecule has a charge of negative 2, and we know that oxygen has a charge of negative 14. So this means that the value of chromium minus 14 has got to equal negative 2. Whatever chromium is, you subtract the 14 of the oxygen, that's going to give you negative 2. That means that chromium equals positive 12. 12 minus 14 equals negative 2. So the value of the chromiums total has to be plus 12. But there's 2 of them. And so that means each one has to have an oxidation number of plus 6. Right? So you might want to just stop and kind of pause and think about that one. Let me go back and say it one more time. Okay, so we have an overall charge on this ion, this molecule, of 2 minus. Oxygen has a charge of negative 2, and there's 7 of them. So that means oxygen overall in this molecule has a charge of negative 14. Chromium plus the oxygen has to equal the overall charge on the molecule, which is 2 minus. So this means that the value of chromium minus 14 equals negative 2, and just do the math on that, and you get the chromium equals plus 12. That's the overall charge on the chromium, the Cr2. Since there's 2 of them, though, to get the oxidation number of each chromium, you have to divide by 2. Each one is worth 6. It has a value of 6. So since there are 2 chromium, then each chromium equals plus 6. So the oxidation number for oxygen doesn't change. It's a fixed number. It's minus 2. And for the chromium, we just figured out it's a plus 6. Okay, so that's how you do that. Okay, the rest of them are easy. Chloride minus the chloride ion, that's not a trick question. It's a minus 1. The chromium 3 plus, that's not a trick question. It's a plus 3. And the chloride is a diatomic molecule in its natural, most stable state, and so it's going to have an oxidation number of 0. So now we go ahead and figure out the oxidation numbers and reduction. So for chromium, it goes from positive 6 to positive 3. That's a reduction. And the chloride goes from negative 1 to 0. That's an increase, so that's an oxidation. And that's how you do these. Most of them are pretty straightforward. Some of them can be a little tricky until you get used to them. Okay, so now we're going to learn how to balance a redox equation in acidic solution. I'll explain that in just a second. So balancing redox reactions requires both mass, the number of atoms of each element, and the charge to be balanced. If you remember way back when we were just doing basic balancing equations using the box method or by counting the atoms on each side, we were only balancing for atoms. And the reason is the charge was already balanced, but we didn't know we even had to think about that. But now we do. So now you have to balance for both mass and the charge that has to be balanced. So the method used for balancing redox reactions is called the half reaction method. We call it the OOE method, okay? And we'll learn what the OOE stands for here in a second. So the first step is you divide the chemical equation into 2 half reactions, an oxidation reaction and a reduction reaction. 2, you balance the other elements, in other words, everything except oxygen and hydrogen. 3, you balance the oxygen by adding H2O to each side as needed. 4, you balance the hydrogens by adding hydronium ions as needed. 5, you balance the charge, that's the electrons, so you add electrons to each side as needed to balance the charge, the electron, the overall charge of the equation. 6, you multiply each half reaction so that the charges E cancel out. 7, you add the half reactions just like we did in Hess's law. And finally 8, you just check your work. Check to make sure the charges are balanced. Okay, so let's go ahead and work through one that's on your assignment. We did this one in class. All right, so balance the following redox reaction in acidic solution. Note, this is an incomplete reaction called a skeletal reaction, but that does not affect the balancing. In other words, you'll notice you have oxygen on the left, but none on the right. So that's going to work itself out as we balance the equation, the fact that there's no oxygens on the right. That's kind of, this is one straight out of your book that I'm giving you, so you can review this one in your textbook. Okay, so first, divide the chemical equation into two half reactions, an oxidation reaction and a reduction reaction. All that means is you want one reaction that has the CRs in it and a second reaction that has the CLs in it. So we're going to go ahead and do that. So the chromium is the reduction. So that Cr2O7 2- produces Cr3+. So you just took out one of those from the left side, one from the right side. You put it into a single reaction. That's the reduction reaction, okay? Okay, now we're going to do the oxidation, and that's the one with the chlorines in it. So chloride produces a Cl2. All right, so straightforward enough. You just take out you just match up the Cl and the Cl and the Cr and the Cr to do this. So follow the balancing process for each half reaction separately. So we're going to take the first one, the chromium reaction first. So step number 2, balance the other elements except oxygen and hydrogen. So there we go. In order to have the chromiums balanced, we have a Cr2 on the left, so we have to add a coefficient. Remember, you can never add a subscript here. You just add a coefficient, and that's going to make it 2 Cr on the right. So you have 2 Cr on the left, 2 Cr on the right. So you've balanced everything except the oxygen and the hydrogen. Now, so you balance the chromium. Step 3, balance the oxygens by adding water to each side as needed. Well, you see you have oxygen on the left side of the reaction up above, and how many do you have? You have 7 of them, 7 oxygen atoms. So you're going to need to add 7 water molecules to the right side so that you have 7 oxygens on the left, 7 oxygens on the right. And it's at this point I always pause and say, don't try to understand why this is working. It just works, okay? It just does. All right, so now we've taken care of step 3. We've balanced the oxygen. Step 4, we balance the hydrogen by adding hydronium ions. We're going to write them as H+, not H3O+, as needed. So how many hydrogen do we have over? Well, we have 7 times 2 is 14 over on the right. You can see that in the equation up above. We have 14 hydrogen. That means we're going to need to add 14 hydronium on the left. So it doesn't matter that one is an H and the other is an H+. It doesn't matter. They're both hydrogens. So 14 H+, 14 H's on the left, 14 H's on the right. So we've now taken care of step 4. So since this is an acid reaction, balance H using hydronium ions. In a basic reaction, if there's a slight difference, you would use hydroxide ions, but we won't talk about that today. That's a little too much information for one lesson, so we're just going to go ahead and do the acidic solution here. Now you balance the charges E, the electrons. It's not just the electrons, I shouldn't say that. It's the charge, the overall charge. So watch how we do that. So if you look over on the left side, you have 14 positive charges, those 14 H pluses. You have a -2 charge on the Cr2O7 ion. That's a 2-. That means your total charge on the left side of the arrow is 14 minus 2 is 12. Okay, total charge on the left. Now we go over to the right. You have chromium at 3+, and you have 2 of those, so that's a 6+ charge. The water molecule doesn't have any charge to it, so you can ignore that. So you have a +12 charge on the left and a +6 charge on the right. You need to get those charges to be balanced, to be even. And you got to do it by adding electrons, which are negatives. They're negative numbers, negative charges. So where are you going to add the electrons so that you can get those two to be even? The answer is you put them over on the left. You put 6 electrons on the left. So the +12 up on the top there, -6, which is the electrons are negative, gives you a +6. 12 minus 6 is 6. And that equals the +6 over on the right side. So that's how you balance the charge of the overall reaction. So compute the total charge on each side and add electrons to the more positive side so that the charge is balanced. Okay, now we're going to go back to step 2 and we're going to do the other reaction, the chloride reaction. So there it is. So to balance that, you had a Cl minus on the left and a Cl2 on the right. So you have to put a coefficient of 2 in front of the chloride. So now you have 2 Cl's on both sides. Now the rest of it's going to be easy. Balance the Cl. We just did that. Okay, now balance the O by adding H2O to each side as needed. Well, there's no oxygens, so we don't need to do that step. Skip this. There are no oxygen to balance. Step 4. Balance the hydrogen by adding H plus as needed. Well, there's no hydrogens. So skip this. There are no hydrogens to balance. Step 5. Balance the charge. We do have to do that. Okay, so we have a -2 on the left. You have chloride ion at -1 and you have 2 of them. So that's a -2. Over on the right, it's a neutral molecule. It's 0. So what are you going to do to balance this? You're going to have to add electrons, 2 electrons to the right side. So now you have a -2 on the left side and -2 on the right side. So now that's charge balanced. Now we put both equations together. So multiply each half reaction so that the charges, the E minuses, cancel out. So there's the 2 equations. And you see on the first one, you have a 2E minus, the chloride one, the one we just did. For the first one that we did, the chromium one, you have a 6E minus on the left side that we computed earlier. So you need those 2 charges to be the same. So what you're going to do is take the first equation there, multiply it by 3. So 3 times 2E minus is going to give you 6E minus. So both equations will have a 6E minus. One of them is on the right, one of them is on the left. Remember, though, that when you multiply that by 3, that first equation, you have to multiply everything in the equation by 3. The Cl2 and the Cl minus. So there we go. We have that same equation. So you multiply this reaction by 3 to get 6E minus. This one you don't have to multiply by anything. You already have the 6E minus. So what you get down there for the first equation is the 6E minus, but you also had to multiply the Cl2 by 3, so you get 3Cl2, and you had to multiply the 2Cl minus by 3, so now you get 6Cl minus. Then the bigger equation, the longer one, stays the same. So now you have 6E on both sides. Okay, so we're going to add the half reactions. So you see the 2 reactions don't have anything in common except the 6E on the right and left sides of the reactions. So you're going to cancel those. Nothing else in common, so you're simply going to add those. Okay, so you have 14H plus Cr2O7 plus 6Cl minus on the left, and over on the right you have 2Cr3 plus, you have 7 H2Os, and you have 3 Cl2 pluses, and that is your final balanced reaction for both charge and number of atoms. So number 8, just check your work. Make sure the charges are balanced. So this is the final balanced equation. The equation is balanced for both charge and number of atoms. Okay, and that takes care of this lesson on balancing redox reactions and how to assign oxidation numbers.